I hope you can hear me. Welcome to the week 11 assignment solution live session for the course Bonds and Bands in Solids. And let's start with our first question. Now, in the molecular orbital picture of a hydrogen molecule, which of the following is correct? Now, for hydrogen molecule, let me draw the configurational coordinate diagram where the electronic energy surface for a hydrogen molecule goes as follows. Let's say this is energy, which is a function of distance r, or let me just call it capital R, and this is the r is the distance between the two atoms. Now in practical sense, the hydrogen molecule should be stable at some bond length and should have a minima, and then as the distance between the two atoms is increased, it should approach the zero value of energy, because now there is no interaction at large distances. There is no interaction between the two atoms. But what molecular orbital picture depicts is shown in a different color, is as follows. It does go through a minima, but it doesn't saturate at zero value. In fact, it saturates at a finite energy value. Let's call it E naught, which is finite and which is counterintuitive. Simply, the reason being that one can write wave function for a hydrogen molecule as follows. That psi can be written as resonance of now for a hydrogen, let's say I depicted this, which has one electron, and all these electrons are a part of this bond. Now let's say if all the two electrons are shared by one hydrogen atom, then that would become H minus and H plus. Another scenario may be the reverse of first one, and rest of the two are that since two electrons are similar, therefore we can have, let's call it H1 and H2, H1 and H2, and this. Now these two states, or these two possibilities in which the hydrogen molecule exists, are the ionic states, and where the two electrons are shared equally by the two atoms, it's the covalent configuration or covalent state. Now even at large distances for hydrogen molecule, the two states will remain intact, because now let's say if the distance between the two atoms is increased, it will be at the same state as before, because I minus and I plus are still present in the system, and in the same case H1 plus and H2 minus will be present in the system. So the contribution from these ionic states will be constant in such a depiction of resonance picture of hydrogen states, and therefore the binding energy at large distances will still be finite and will not vanish and become zero. So in that sense, the molecular orbital, the correct solution for the following question would be the binding energy at large distances between the atoms would be positive, right? And because of this presence of ionic states in the material. Now second question says that the resonant wave function of hydrogen molecule in the ground state can schematically be written as. Now if we write the resonant wave function for hydrogen molecule, it would be a combination. Since ground state consists of a singlet state and triplet states, it can be written as ground state wave function now this is the first atom having a minus charge, second atom plus charge, and then next would be reversed, and two contributions from the same because of the covalent states. This becomes H1 and H2. Yes. Now this becomes the resonance picture for us. Now let's find out the resonant wave function for hydrogen molecule will be for sure not the first two, because these are two nothing but the singlets and triplet states, the original ones. And ground state is doesn't consist in the sense there are total 6 configurations, out of 4 are in the ground state, so the 6th will not be correct. And since also the normalization constant in third and fourth is 1 by root 3, which can only become if we have like 3 states, which is not correct because we are having 4. Okay, so the normalization constant given in option 3 and 4 is not correct, and rest only we are left with only one option, that is option 5, that matches with our option, but the factor to the states which we are seeing is different.
No, actually, it is multiplied and divided by root 2 root 2 something. I mean, somehow it is multiplied with root 2, 1 by root 2.
1 by root 2. Okay, if that is the case, then we are this should have been 1 by root 2, 1 by root 2, but nonetheless it might be a typo here, I'm guessing here, but but nonetheless out of all these, the rest 5 are for sure not the correct options, since we are only left with one, and it matches with our the ground state of the function, except for some prefactors of in front of the states. Might be a typo here, which I predict. So the correct option would be option number 5 here. So moving on to question number 3, the Coulomb repulsion integral U in the Hubbard model. Now this Coulomb integration Coulomb repulsion integral U is independent of the distance between the sides. Now this comes as a part of the postulate of the Hubbard model, because it's a single band model and consists of only on-site interaction energies. And consists only the overlap of single bands. So let's say if we have a chain of atoms, then whatever the electron present at position 1 will only feel the interaction of another electron when it comes to this position. So if we have a system, let's say another scenario in which the electron is present at some other position, now these two states or these two configurations will be degenerate. So or in another sense, we can say that if one electron hops from one side to the other and creates a positive charge, let's say at this side, and positive charge negative at the other, and let's say another scenario, and another scenario in which the distance between these two entities are different. Let's say we have now 3 atoms in between. Now still these two states will be degenerate because we are considering only the on-site interaction energies, and therefore the Coulomb repulsion integral in the Hubbard model is independent of the distance between the sides of the chain, and the rest of the 3 postulates, that decreases, depends, and increases with distance, are not right. So Coulomb repulsion integral is independent of the distance between the sides in the chain. Now question number 4 is similar to the question number 1, which we just solved above, which says that molecular orbital theory fails to dissociate the hydrogen molecule, describe the hydrogen molecule correctly, as the ground state, as we wrote earlier, the hydrogen molecule, this is nothing but H2, can be written as a linear combination of these states, let's say H1 and H2, plus and minus. Let me just put a circle not to confuse with the plus sign, and two equally contributing covalent states. Now, as we just saw earlier, that these ionic states still maintain their identity at even large distances. So these two states out of the four total states contribute to this linear combination, and therefore it is because the equal contribution of the ionic as well as covalent states to the correct resonance picture of the molecular molecule theory to describe hydrogen molecule. So it's only because of these ionic states and they contribute equally to the final resonance picture, and that is why the reason that hydrogen molecule is incorrectly described in MO theory. So the correct option would be option number 1. Now moving on to the next question. Next question says that at very high pressures an insulator can undergo a transition to a. Now insulators in general, if one thinks of an insulator, is that the orbitals of the individual atoms present at the, let's say, different position do not overlap much or at all, such that there is no electronic conduction into the system. But if one applies high pressure, let's say in hydrostatic pressure at all sides, then these atoms would come closer to each other, leading to interaction of these orbitals and overlap of these orbitals, which means that now overlap has increased and electrons can undergo conduction from one side to the other, leading to insulator nature to a metallic nature. So at high pressures an insulator can undergo a transition to a metal. In general, one can say a metal, but provided the extremely high pressures, even that could go to superconducting states as well. But in general, if we talk about to say safe, we say that insulators turn to metals. Now question number 6 is the following, that for two degenerate orbitals of an atom, what can be said about the spatial part and the spin part of a singlet state? So now this can be answered in the following way, that one can write the final wave function, let's say wave function corresponding to n particles of a system, whatever 1, 2, 3 and so on, can be written as a product of spatial part and spin part. Now for Pauli exclusion principle to be satisfied, one of the spatial part or the spin part has to be symmetric and other has to be anti-symmetric. So for a singlet state we have opposite spins, and therefore at same site two spins of same nature cannot be present. So for a singlet state the spin part has to be asymmetric, has to be or anti-symmetric, and therefore the spatial part becomes symmetric. So spatial part is symmetric and spin part is anti-symmetric for a singlet state. So the spatial part will be symmetric, but the spin part will be anti-symmetric. Now next question is the opposite, that what can be said about the spatial part and the spin part for a triplet state. For a triplet state one has the same spin present in the system. So for a triplet state, the spin function or the spin part becomes symmetric or has to be symmetric, and therefore the special part or special function becomes antisymmetric in nature to preserve the Pauli exclusion principle. So special part is antisymmetric and the spin part A is symmetric. Correct would be third option. The special part is antisymmetric and the spin part is symmetric, spin function is symmetric. Now next question, that question number 8, for a half-filled Hubbard model of n sites in the large U by T limit. Large U by T limit means that there's large on-site electron repulsion, and therefore electrons will be confined to their own site. And let's say we have different sites, and these are n in numbers. And for a half-filled Hubbard model, let's say every site has one electron, and one electron to it. Now this electron can be upspin or downspin. Now since we have two possibilities at each site, and same two here, two here, two here, and this goes for n sites, so number of possibilities we have are nothing but 2 raised to the power n. So the correct option, that number of possible low energy states, would be 2 raised to the power n. Now the value of Gutzwiller variable for a non-interacting system. So Gutzwiller variable, or this theory, just take page. Now Gutzwiller proposed this variation method to solve the Hubbard, or to estimate the Hubbard model in 3 dimension, and the trial wave function in this particular approach is given by, where G is known as Gutzwiller variable. This is written as C0, which is a vector in front of ground state, is a linear combination of all these states multiplied by Gutzwiller variable G, psi 1, G square, C2, psi 2, and so on. Now according to this approach, G can take values between 0 and 1, and when G is equal to 0 and G is equal to 1, so we have 3 cases. When G is equal to 0, we have completely magnetic picture, and when G is equal to 1 means non-interacting system, and when G is in between these two extremes, it is the correlations are present, or correlate, or when we say correlated interactions. So for a non-interactive system, this Gutzwiller variable takes the value G is equal to 1. Now this particular value of G is a part of the approach, and so there's not much rigorous explanation to that. So G is equal to 1 for non-interacting system in Gutzwiller variational approach to solve the Hubbard model in 3 dimension. Now question number 10 says that a system of 2 hydrogen atom has 6 possible states. How many of them are singlets and how many of them are triplets? So this can be written, let's first write the 6 states of the system. First, now let me just start with hydrogen molecule, two hydrogen atom connected by a bond. Now the two electrons between or shared by these two hydrogen atoms can be written as follows: that the spins of the two hydrogen or the electrons present on the two atoms are in the same direction as a triplet state, or they can be both down another state, or a linear combination of state which is still triplet, H1 down and then constructively with. Now these three are there's one more to it, a normalization constant multiplied by H up, H down, the subtraction H down, H up. Now these four states shares the electron equally to each other, and therefore we have four covalent states. 1, 2 and 3 are triplets, where the fourth is a singlet. But also to this there are two more states where the electrons are completely transferred to one of the hydrogen atoms. Now these two states, whenever the electron is transferred, so they have to be paired, and therefore we have the state 5th and 6th, and these are both singlets again. So the question is how many of them are singlets and how many are triplets. So we have 3 singlets, namely 5th, 6th and 4th, and 3 triplets as well. So the correct option would be option number A, but since it's given one triplet, there's a typo. It might be one set of triplet, one set of 3 triplets it should have been. So option A is the correct option. We have 3 singlets and 3 triplet states. Okay. Now question number 11 says that, now let us first now in the above question number 10, let us first draw them to the energy scale. Let's say this is the energy, and let me denote the set of triplet states. Out of these 6 states, 4 are degenerate and 2 are in higher energy, which are still degenerate, and separated by the Coulomb repulsion energy U. These 2 states are the states 5th and 6th that we just described above, that these 2 singlet states, and we have states 1, 2, 3 and 4. So this is the picture where there is no perturbation to the system, or there is no transfer term is absent. So this transfer term T, or the hopping, is nothing but the perturbation. So when transfer term is absent, we have such scenario. So let me call it scene 1. So in scene 1, the ground state, that is the ground state of the system, is of 2 hydrogen atoms, is 4-fold degeneracy. We have 1, 2, 3 and 4 is a 4-fold degenerate system. Now out of these 4-fold degeneracy, state 1, 2 and 3 were triplets, and 4th state was a singlet. So we have 1 singlet and 3 triplets. Again there should have been one set of triplet, one set of, there's a typo, one set of 3 triplets. So the ground state is 4-fold degenerate, but having 1 singlet and 3 triplets or one set of 3 triplet. Now the next question, when it says that when the transfer term T is turned on or the hopping interaction is started in the system, the ground state of the two hydrogen atoms, that is this one, what is the variation of this thing? So let me just draw the ground, the variation in this way. So if transfer term or the hopping is on or hopping is there, then singlet state becomes more stabilized as compared to the set of triplets, because one can have more number of exchanges in the singlet state. So the transfer term T is on, we have a non-degenerate singlet state as the ground state, because singlet state becomes stabilized under hopping. So we have a non-degenerate singlet state as the ground state of the system. Now question number 13th is just a consideration that consider a half-filled single band Hubbard model, and configuration 1 says the atom at site 5 has no electrons, while atom at site 6 has 2 electrons, while in configuration 2 atom at site 3 has 2 electrons and atom at site 8 and it has no electron. So it's just a scenario 3, 4, 5, 6, 7 and 8. Let's just name these sites. In the first configuration it says that atom 5 has no electrons, so let's say there's a positive charge, and atom 6 has 2 electrons, so it becomes negatively charged. This is become configuration first. And in second configuration site 3 has 2 electrons, so negative charge moves here, and 8 has no electron. This becomes the second scenario. So as we know that the configuration or this Coulomb repulsion energy, Coulomb interaction energy or Coulomb repulsion energy is independent of the distance between the two sides that we are considering, as we have seen in our earlier question as well. So because of this Hubbard model is a single site model, so Coulomb interaction is independent of the distance between the two entities. So correct option would be, which of the following is true? A would be the interaction energy is U, the Coulomb interaction energy U will be same for both of the configurations, that is for 1 and 2 there will be same Coulomb repulsion energy. So that is mostly a drawback of the system. So correct option would be option number 3. And so this is how we have finished solving assignment 11. So if there are questions, one can unmute and ask, or not, we can park the present discussion here. Hello?
Yeah, it's okay.
Okay, then let's close the session. Okay, and we'll meet on, and there's just a reminder that the next session is on 24th, that is Monday 7 p.m. rather than Tuesday 7 p.m. because
Tuesday is Diwali.
yeah, so I have I'll try to convey this message on the portal, but since you have joined, so Monday 7 p.m. would be the regular session rather than Tuesday, just to remind. Okay, that would be the final session for this course, and after that there will be an exam on 29th, I hope. I think so. All right. Okay, so we'll close the session now. We can log out.